Good afternoon, everyone. It's great to be here today. I've found this topic very interesting to work on, and I hope that you share my enthusiasm for it and you find it useful today. So at PDL, we've developed a technique for completing high cycle fatigue assessments on deck-mounted structures. And basically, it's to DNVGL RPC203, so that's the DNVGL fatigue code, provides various SN curves, etc. There's no particular reason you couldn't use this technique with other codes. That's just what we've used to date for the stuff we've been working on. And it's efficient in the sense that it's quite quick to run and get results. It's efficient in the sense it's quick to post-process. Hopefully I'll show you that in a bit. And also it minimizes undue conservatism, basically, so allowing you to create efficient designs. And it's been used to gain certification from DNVGL on multiple projects and in recent years. So I just wanted to show you some images to start off with. So all of these structures are mounted on ships. Top image is showing a sliding deck, or Mobo deck is its nickname because it holds a Mobo type pump. But basically it's in the middle of a ship and there's a moon pool. And the bit in red extends, slides over the moon pool. It can be used to support part of a riser. When not in use, it retracts out of the way. Bottom left is a maintenance tower. So this is used to store and assemble BOP stacks. And bottom right is an ITF, or tension frame. And I'm going to talk a bit more about that in the next few slides, so I won't go into detail now on that. But basically, all of the images on the right, obviously they're contour plots. They're not showing stress, they're showing accumulated fatigue damage. Which is the output of the technique. If anybody who's not familiar with the concept of fatigue damage, then all it is the number of loading cycles you expect to get divided by the number of cycles to failure. Cycles to failure being calculated using an SN curve and a stress range. So this is what we use to post-process. So I'm going to concentrate on in this presentation the ITF, or intervention tension frame, to give it its full slightly tongue-twisting name. And the ITF is basically, it provides a platform for one intervention equipment. So you can imagine this is actually used, when it's in use, it's attached to a multi-purpose tower, or MPT. So you imagine a large crane in the middle of the vessel. I've got a picture in a minute, but there's a big crane, and you attach this to it, and then the entire thing is heave compensated. So you imagine you've got this 110-ton structure. The whole thing is heave compensated, and then it supports a riser hang-off load of up to 500 tons. And while it's heave compensated and supporting the riser hang-off load, you can basically access the ITF and you can perform one intervention. So that could be coiled tubing, it could be wireline, whatever. But the point is you're on the ITF and you're performing some sort of one intervention. And so when not in use, it's actually lowered down, you disconnect it from the multi-purpose tower, and then you put it on a pallet, and you wheel it somewhere else on the vessel, and you fasten it down, and that's stowed there. So some images to kind of give you some context. So I guess we worked on 3 ITFs at PDL. So as you can probably see, the ITFs, obviously we worked in the context of a consultancy performing this analysis. We're working for Osbit, which is a company based down in the northeast, responsible for design and getting these structures fabricated. I know they actually won an award for the ITF, Subsea Innovation Award. And all of the work was ultimately for Helix Energy, who, as you can see, own these vessels because they've got it in nice big letters on the side. So there were basically 3 versions of the ITF, 3 sort of flavours that we worked on, and they were for Siem Helix 1 and 2. So they're identical one intervention vessels. Nominal operation, part of the world initially anyway, is Santos Basin off Brazil. You can see that's the top image. And you can see the multi-purpose tower in the centre, and you can see the ITF in its stowed location. And then bottom right is the Q7000, which is a semi-submersible, initially going to the North Sea. And these are, so basically we worked on 3 ITFs for Siem Helix 1, 2 and Q7000. So what are the challenges? What are the challenges when you're completing a high cycle fatigue assessment on these kind of structures, so the ITF? So I guess really the main challenge, which many of you are probably familiar with, is, the main loading this is going to be subjected to is due to the vessel motion. So due to waves hitting the vessel, it rolling around and then being accelerated. And obviously, in the context of that, we've got to somehow model our waves, like our long-term sort of distribution of waves, heights and periods. So obviously, we can have all different sea states and different waves within the sea state. The vessel can also have different headings. The vessel can also be doing different things. It could be transiting, could be stationary, operating on subs. Also, it can have different drafts. And then the structure could obviously be operating. It could be slightly different types of operations, different riser hang-off loads, perhaps. And then obviously it can be stowed. So its stowed location is very, very different to its operational location. And it's very loaded in a very different way when it's operating. It is truly a tension frame. It is mainly loaded in tension. When it is stowed, it is basically a tower. It's sea fastened somewhere else on the vessel. So all of this means it's A, how to model all of those different loading scenarios, and then B, how to actually know where your fatigue critical locations are. So I guess something that I've done, and I guess maybe many of you have done as engineers, is if you've got a simple loading cycle, then you might model that. You might apply the loading in ANSYS, see what kind of stresses you get, see what stress range you get, pick a fatigue critical location, do some Excel calculations. But the problem here is we can't pick like a representative load case, so there's too many. So if we were to pick one, then it wouldn't be the highest stress wouldn't necessarily be the fatigue critical location. It would just be the highest stress for that one-off loading condition, but there's all these others. So really we have to kind of perform the analysis for the whole structure. And basically also like what we found is, oversimplification leads to over pessimistic results, can't design an efficient structure. So you have to go to quite a high level of complexity to design something that is efficient, not waste load of material. So this is the process we came up to basically achieve what we wanted to do. So 6 steps. Number 1, set up an FE model, ANSYS, mechanical, workbench, shell model, solid model. Number 2, run unit acceleration load cases. So see how the structure responds to surge, sway, heave, roll, pitch, yaw. So apply acceleration, see what stresses you get. Number 3, extract the results files. Number 4, feed them into an in-house APDL macro. So that's using APDL to basically take that information that you've generated using ANSYS Mechanical and then calculate fatigue damage for all of your loading bins and calculate your accumulated fatigue damage. Number 5, plot that as a contour plot like you've seen. Number 6, use that to post-process. So obviously the most complicated bit is the macro, and I'll do a bit more detail on that in a bit. But to start with, we'll have a quick look at the FE model that we used, or some of the FE models we've used. So this is obviously the ITF. This is the global shell model that we use to capture the general response in a global sense. See two slightly different versions of the ITF, slightly different sea fastenings, but they're both modeled using shell modeling. And obviously we modeled it in the sea fastened location, also in the sort of operational location, just slightly different boundary conditions need to model sea fastenings in the sea fastened location. So a bit more detail on the shell model. So you can see top right, you can see some detail in the top crossbeam, some of the stiffeners. And so you can also see some of the sea fastenings, lower crossbeam. And obviously a shell model, it's not always good enough. It's not always detailed enough for all of the regions. So sometimes we do some solid submodeling. Again, ANSYS Mechanical, it's pretty easy. Just, you can link it up automatically, obviously. You can bring in your displacements from your shell model into a solid model, do your submodeling. So on the 2 sort of sizes of submodel here, on the left, what you're seeing is a spool piece. This is where the riser attaches to. This sits in the lower crossbeam of the ITF. On the right, we've got a very localized submodel. So we've just got a complicated corner detail, which has some complicated welding detail. So we've modeled the welds and we've modeled the corner detail because it's just, a weird connection that we can't capture else otherwise. And I think we can model, obviously you can model the welds as accuracy one. If it's a fillet weld, we can model the weld and then model a small gap between the plate and the next plate, so you get the actual load transfer through the fillet weld. Okay, so there are EFI models. We run the unit acceleration load cases. It's very simple to do that part. Then we're going to extract the results files and we're going to feed them into our APDL macro. So macros don't have nice images, so just have like a little chart. But I guess the first step is basically we have to formulate our loading breakdown. So the basis of the macro is you, first of all, just break a loading down into lots of bins, into a time series if you like, or like lots of bins that represent basically waves. But waves also coupled with the fact that it's this wave, but also it's this vessel heading and it's this operational scenario. So that's the basis. We have to formulate that. And we do that using the wave. The wave environment is modeled using a scatter diagram. So if you're not familiar with a scatter diagram, it's just a table that tells you the long-term distribution of sea states. So it says over a long period of time, a year or longer, you'll get these sea states. You expect to see these. This is a probability. And we use that in conjunction with short-term wave theory to actually say in that sea state, you're going to see these particular waves. So, okay, we've formulated our loading breakdown. Maybe we've got 100,000 load cases now we need to consider. That's a quite common number because, there's well, I'll talk a bit more in detail in a bit, but it's a lot of things, a lot of waves to consider, a lot of scenarios. So the next step is to actually calculate damage. So for each loading bin, we want to calculate fatigue damage. So we know what waves hit our vessel. And then we could use REOs, response amplitude operators, which tell us if this wave hits our vessel, then what acceleration do we get at a point on our vessel? Okay, so we know that. If we get this acceleration, what stress do we get? Well, we run an FE model that tells us that. So we know that. So we know stress range. And then we can calculate cycles to failure using an SN curve and calculate fatigue damage. I guess this is a slight simplification because what you have is lots of nasty sort of wave phasing effects that you've got to account for. But yeah, it's kind of beyond the detail of this presentation, but that has to go into that calculation as well. Say you've got like basically, superposition of different effects at once. So, okay, now we've calculated fatigue damage. We've done that for every single loading bin, 100,000. We just add it all up using minus rule. And now we've got that information stored. So now for every point on our analysis model, every node on our analysis model, we know the total accumulated fatigue damage. We also know how we've got to that fatigue damage. So we can potentially look at how we've got there as well, which I'll talk about a bit later. So how do we get to 100,000 plus loading bins? So if you take a look at this, hopefully it gives you some indication. So just to show this is like a way of breaking it down. So first of all, say what design environment you're in. Could be North Sea, could be off Brazil. So here we're Magnusfield, so North Sea. What kind of vessel's loading scenario it is. Is it transiting, not transiting? What's the structure doing? What's the vessel heading, sea state, wave height? So you can see if you follow that through, you can end up with a lot of subdivisions, especially with the sea states and the wave heights and periods. Again, just in case that if you're not familiar with a scatter diagram, this is a scatter diagram just from DNV, GL, one of the standards. And yeah, just telling you probability of different sea states. And just an illustration here. So this is just showing, like this is for the ITF. This is the actual number of loading bins we use for a particular run for a particular ITF. So we used 200,000 plus loading bins. And this is don't need to worry too much about it, but it was just a plot to show the magnitude of like loading bins that you are considering, and the data you have to process. We plotted them off SN curves in this case. It's quite a useful way. You can get some information from that because you can like see what your biggest stress range is and how that falls in relation to your SN curve. It's quite a useful output, but that's is really an illustration. Okay, so we've done the macro. We know our fatigue damage, so now we're going to post-process. So this is the kind of output we get. So obviously it's a contour plot you're familiar with. It shows fatigue damage in this case. So initially what we'd do is as you're probably familiar with, you get lots of different SN curves for different details. So for certain welds, you have more onerous SN curves that you have to use than for other welds, or for parent plate. So initially we just choose the most onerous SN curve, we just plot fatigue damage for that. And then we say, okay, well, any area that passes that with that SN curve, it's going to pass the whole assessment. So that allows us to write off huge areas of the structure immediately. You can see here, there's 2 areas that haven't passed, but it doesn't mean they've failed. It just means that they've not passed with that screening SN curve. So then we'll zoom in and we'll look at them in a bit more detail. I should say obviously all the numbers are removed, but for fatigue damage, basically, if it's above 1, it definitely fails. If it's below 1, then it may pass, but you normally apply a factor of safety, so 2, 3, 10. So depending on that, it could be 0.1, might be your limit maybe. So these are the 2 regions we're looking at from the shell model. So just to say, all right, like zoom in a bit more detail, what SN curve do we actually need to consider? We've already calculated all that information. We've calculated the fatigue damage for every SN curve, so we just replot it, and we can say in this case it fits well in, it passes, not a problem. And again, for you can see here, for post-processing using the submodels that I mentioned, just these are some of the outputs. The slight technique that we'd use to post-process is like maybe a little bit like hotspot method, often used, especially with solid models. But yeah, it depends exactly what your modeling technique is. This is not the ITF, I'm afraid. It's a different structure, but I'm a bit sad, and I thought it was quite a nice weld, detail to model. So I just put it in anyway. So yeah, it's just showing you can go to quite a lot of detail. So in this case, it was a fillet weld, and then we had probably the gap between the plate, and you could go in and you could look at here, you're looking at the sort of toe, but you could look at the root as well, and you could do all that sort of very in-depth analysis for a particular critical detail. So another interesting thing we can do is, because of the way we've computed it, we can actually do whatever breakdown we want using the contour plots. So usefully here, we can say, okay, what's the fatigue damage accumulated, stowed and operational? So it's quite interesting for the ITF, because you can see more damage is accumulated when it's stowed. And that's because, it's not necessarily what you'd expect on first thoughts, because the riser hang offload is 500 tons. So you think, well, that's really big, it's going to be really high stressed. So surely that's the critical scenario. But actually, it's designed to be a tension frame. It's very good at taking 500 tons in tension, hanging off the bottom of it. When it's stowed and it's C-fastened, it's less designed to do that. You obviously can do it, but it's not. It's nominal operating scenarios. So actually, it's more fatigue critical for it. The other thing to say is, again, using this particular code, you don't do a mean stress correction, because it is built into the SN curves of mean stress correction. You could do one, that wouldn't be a problem at all, but it just depends on the SN curve you're using. And obviously you can imagine when it's operational, there's a huge mean stress, but that's already accounted for by the curves. So it's kind of a bit, if you were to look at it from a perspective where you were doing a mean stress correction, then you'd see a slightly different split, but that's down to the code that you're using and the sort of interpretation method, which is obviously prescribed by DNVGL in this particular case. And this is showing what you could do for an individual point. So we go to a particular point, fatigue critical point on our structure. We could take a node, and then we could do some more interpretation. So we can say, all right, where do we get our fatigue damage? What C states? So we can pinpoint the C states. And that, in this case, it's fairly obvious information perhaps, but it's not always going to be like that. Because here we're getting a high response with periods C states which have lots of wave periods that correspond to near the peak vessel response. So okay, that's as you might expect. But A, it's a good check, and B, it doesn't obviously you don't always get exactly the response you expect. So it's just these are just really ways to say you could use this technique to obviously do the assessment, and it's an efficient way to do that. But furthermore, you can actually use it to drill in and see what's driving your structure, which is quite helpful. Especially if you want to do some redesign because some bits are failing, or you want to pinpoint, for this case, we pinpointed that the stowed is quite fatigue critical. So then maybe you want to do some different C fastenings, for instance, that's going to support it better when it's stowed. Okay, so quick summary. So number 1, set up our EFI models, answers mechanical. We had a look at how it responds to different accelerations, so to say here, roll pitch yaw. Then we use an APDL macro to calculate fatigue damage. And this works on the basis that you can break down your fatigue loading into lots of individual loading bins, so typically 100,000 plus. And each fatigue bin corresponds to a particular wave, scenario. You can then post-process using contour plots. And yeah, like I said at the start, we have used this to sort of gain certification for multiple projects. So I hope that's been interesting for everybody. And yeah, invite any more questions that anybody has. Thank you for your time.